Another type of test design technique that I think comes up whenever I'm exercising complex business logic is decision tables. Sometimes people also do the same type of test design using other objects like decision trees. It basically comes out to the same type of thing. Imagine you're confronted with a project where the requirements read something like this. Step 4, who is considered a parent in this step? Read these notes to determine who is considered a parent for the purpose of this form. Answer all questions in step 4 about them, even if you do not live with them. Are you an orphan, or are you or were you until the age of 18 a ward or dependent of the court? If yes, skip step 4. If your parents are both living and married to each other, answer the questions about them. If your parent is widowed or single, answer the questions about that parent. If your widowed parent is remarried as of today, answer the questions about that parent and the person whom your parent married, your step-parent. If your parents are divorced or separated, answer the question about the parents you lived with the most during the past 12 months. If you do not live with one parent more than the other, give answers about the parent who provided more financial support during the last 12 months or during the most recent year that you actually received support from a parent. If this parent is remarried as of today, answer the questions on the rest of the form about that parent and the person whom your parent married, your step-parent. This sounds like legal gibberty-goop. This is actually a real statement of a business rule related to the American Federal Student Aid Form. I use this very often when I'm teaching requirements and test design, because this is sometimes the language used to describe the business rules. And if you were charged with programming it, how would you interpret it? There are many, many interesting conditions in this. There's many strange conjunctions. There's questions about or, there's dangling things. So what? What if it's not true? It's not clear. It says what to do if it is true. It doesn't say what to do if it's not true. It's very interesting that people write in this style. It's almost as if a bunch of lawyers had to have a meeting to debate it, and they all came to some consensus with the wording eventually, because all their objections turn into conditional clauses in the middle of the text. Whenever you find yourself with requirements that are described and it sounds like the federal student aid form, it's time for you to consider using a decision table. When we construct a decision table, we basically start by trying to identify conditions. What are the factors that are influencing the logic? What are the input variables, if you will? And then we want to identify what are the actions. The actions are the variable outcomes. So the conditions are like the input, the actions are like the output. The conditions are like the factors, the actions are the variable outcome. And then we relate the conditions to actions with rules. We call the relationship between conditions and actions a rule. So you've heard the term, I'm sure, business rules. Business rules are a relationship between conditions and actions. If certain conditions take place, then certain actions are required. This is how business is run. Once we've established the relationship between the conditions and actions, then we can do something which is called logic reduction, which is where we try to represent that relationship between conditions and actions with basically as few rules as we can. So we try to minimize the number of rules. And then once we've got the rules all lined up and they're all minimized, then what we do is we try to come up with one or more tests for each rule. And a test will be basically a set of conditions that are input and an expected result, which is a variable outcome. Decision tables find themselves in a lot of projects where we're doing application development, anything with business rules, regulations, or systems that tend to have multiple conditions with multiple actions. This is even controls for appliances and furnaces and thermostats fit into this. So decision tables show up all over the place in software engineering. Often they're represented in a tabular form, and one of the easiest tools to use to draw a decision table is actually Excel from Microsoft, a spreadsheet program. What you do in a spreadsheet is for the conditions, you'd assign 1 row per condition. For the actions, well, the variable outcome, you'd have 1 row per action, and then you'd use the columns to represent the relationship between the conditions and the actions. This is an example from Wikipedia of a generic decision table to support troubleshooting activities. So if you take a look at this, the top 3 rows are conditions, that's input. The bottom 5 rows are actions, that's the variable outcome. If you want to look at the columns represent rules. In this case, there are 8 columns with different rules. So there's 8 business rules for this. The conditions in this case are binary, true or false. Decision tables do not need conditions to be binary. They could be an enumerated list, or they could be value ranges. There's nothing wrong with that. Now, in these conditions, if you read it from left to right, the first rule says, if the printer does not print, and a red light is flashing, and the printer is unrecognized by the operating system, then what we should do is we should check the printer computer cable, ensure printer software is installed, and check or replace the ink. So those are the 3 actions we should do if these 3 conditions are true. This is for support desk people to troubleshoot printer problems. Let's look at this rule here. If no, the printer does not print. So in other words, the printer is printing, but there is a red light flashing and the printer is unrecognized, then we've got to ensure the software is installed and we've got to check the ink and maybe replace the ink. The last one here, no. If no printer is not printing, i.e. the printer is working fine, no light is flashing, and no printer is unrecognized, so the printer is recognized, then there's no action to do. There's no reason for a support call. So we read these top to bottom, 1 column at a time for the business rules. So in this case, we have 8 columns with 8 rules. Each one is distinct. They're basically set up in a way that they cannot be optimized further than that. What about the following example? This is an example of a decision table that's used to decide what to do based on university applicants at some fictitious American university. So there's 3 conditions for eligibility. One is the SAT score, which could be high, low, or medium. Do you have the prerequisites, all the prerequisites, part of the prerequisites, the core prerequisites only, or none of the prerequisites? And where do you live? Do you live in state, out of state, or are you from a foreign country? So those are the 3 conditions. And the possible actions are, you're accepted, you're redirected into a new program, you're offered a conditional acceptance, you're rejected outright, and the last one is you're offered a grant, some sort of financial incentive to come to the university. So if we read this from top down, rule number 1 says if you have a high SAT score and all of the prerequisites and you live in state, we're going to accept you right away and we'll even offer you a grant. So that's the first rule. Now, if we look at another rule down here, let's look at the 5th rule. If you have a high SAT score, you only have the core prerequisites and you live out of state, well, we're going to give you a conditional acceptance, but we're still going to offer you a grant. Now, if we go down to rule number 10, there's something a bit different here. Rule number 10 is something that you can see has a star or an asterisk under residency. We read this as follows. If you have a high SAT score and none of the prerequisites, it doesn't matter where you live. We don't care where you live. It's a don't care condition. We're going to redirect you to another program. And if we look at rule number, 17, if you have a medium SAT score, part of the prerequisites, and you live in state, we're going to redirect you, but we're going to still offer you some sort of a grant. So this is a strange, funky business rules about offering grants and redirecting people to other programs. You'll notice rule 20 also has a don't care condition. If you have a medium SAT score and none of the prerequisites, we don't care where you live, we're going to reject your application. So this is how we read this. I guess the last 4 here are pretty similar to the other ones. If you have rule 24, low SAT score, none of the prerequisites, it doesn't matter where you live, you're going to be rejected. So the decision tables, once you've reduced them to the fewest columns you can, so that's basically trying to identify where we can put in don't care conditions, then we basically have a list of the rules that must be exercised to exercise the business logic. So you would need basically one test at least for each of these rules to thoroughly exercise the business logic. In this case, that would be 24 tests to thoroughly exercise the business logic. Now, sometimes when you collect decision tables, they don't look obvious how they're going to be reduced. So for example, if you have this one, this is actually from a customer in Portland, Oregon, a few years back. It was a power utility, and they were looking at crazy business rules that they had to change related to how you treat people who are roommates living in apartments which hasn't paid their electricity bill, and yet it's not the fault of the roommates. So you have some interesting, strange conditions about these things. They have like, do you have a roommate, true or false? Is your accountant default, true or false? Do you have a pending default move-in for someone who's, or non-default move-in, whatever that means, or a default move-in, whatever that means? There are two different conditions for people to move in who might pay the bill. And is the move-out date greater than the move-in date? All of these factors combine to basically say, okay, we will do something different. We're going to create some sort of conditions, invoice things differently, or do nothing. So what happens here is, during an elicitation meeting, these 16 rules were elicited. These rules were then put into a decision table logic reduction tool called E2G Rule Writer, which I'll be happy to put a copy in of my courses. It's a free, although not open source, Java application. It's a little bit old, and it only seems to work well on low resolution devices. But it's a decision table optimizer, really. And what it did was it reduced this table to these 8 rules. So if you take these and apply logic reduction to them, you'll get it down to these 8 rules, which thoroughly would exercise the business logic associated with this requirement change. So logic reduction for systems that have multiple conditions and multiple actions is not obvious and requires sometimes the support of tools. It's interesting to note that if you are ever going to reduce logic, you have to look for two sets of output. So here, false, 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 true, false, 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 true, false. Those two outcomes are the same. Therefore, it might be possible to restate the input so that we have fewer rules. So there might be a logic reduction opportunity. There's certainly logic reduction opportunities if you have only one difference in the numerator. So the unreduced case, you might find a few examples where you'll have the same exact. So if you look at rules 15 and 16, you have false, 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 true, false, 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 true, false. So for basically 15 and 16, you have exactly the same outcomes, but the input for one is false, false, true, true, and then false, 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 true with the don't care. So that can be combined into one rule that says false, false, don't care, true, don't care, for false, 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 true, false. So that's how logic reduction works. When you have the exact same outcome and one bit difference based on the input, you can combine things. And there's, of course, tools that will investigate all of the possibilities to see if logic reduction is possible. If you've studied logic designs of truth tables, you'll realize that this is very similar to the logic reduction problem of a decision table. Here's an example of a decision table made for the business rules of the game Monopoly. It's similar to the example I showed earlier when we talked about user stories. Monopoly is full of complex business rules, and so it might make sense to represent the business logic instead of in the form of a story, which you can do, but it might make more sense to represent it in the form of a decision table, which then becomes more graceful to identify what are the conditions to test. So if we start here, decision tables, so basically the purchase rules of a house is the property must be in a color group, the same player must own all the properties of the color group, no properties in the color group can be mortgaged, houses must be for sale, Houses must be built progressively. That means that you start with 1, 1, 1, then 2, 2, 2, then 3, 3, 3, then 4, 4, 4, and you can never have more than 4 houses on a property. If multiple players are attempting to purchase the house at the same time, then there's an auction, and the highest bidder will get the house. And this basically breaks down into this decision table here. So if you look at, we put the story in the upper left-hand corner just to make it clear. As a player, I want to purchase a house on one of my properties so as to increase potential rent revenues, respecting the house purchase rules. Then we have a bunch of conditions and a bunch of actions. And the conditions would be, are the properties in a color group true or false? Are all the color groups owned by the same player, true or false? Are any color groups mortgaged, true or false? Are any members of it mortgaged, true or false? Are there houses for sale, true or false? The number of houses on the target property, are they less than 4 or 4? And that's the two choices, less than 4 or 4. Are there other properties with fewer houses? This is for the balanced building of them. 1, 1, 1, 2, 2, 2, 3, 3, 3. Are there hotels on the target property? If there's a hotel, you can't put a house. Are there multiple players attempting to buy the same house? Are you the highest bidder? And do you have sufficient funds for the purchase? So those are all the factors. And then the possible outcome is a successful purchase at the target price or at an auction price. So those are basically 3 true or false actions. This is a reduced table. So if you read rule number 11, or not 11, I guess it's full of don't care conditions, but boring one. Let's try rule number 9. So yes, the properties in the color group. Yes, all the properties are owned by the same person. No, properties are mortgaged. Yes, there's houses for sale. Yes, the target property has less than 4 houses. No, other properties has fewer houses. No, hotel in the target property. Yes, multiple players are bidding. Yes, I have the highest bid. Yes, I have enough money to pay for it. Therefore, I get the successful purchase of it, but I pay the auction price, not the target price. So that's an example of a decision table in Monopoly. The idea now is, once you've got the decision table represents the business rules. Then you use the rules to drive tests. And what I would suggest, of course, is to drive at least one test case for each rule, reading it top down in this case. So one test case per rule, at least. You could do more if you want, but one test case per rule would thoroughly exercise the business rules. And that's sort of the beginning. If you have more time, more budget, you then might figure out more test cases to drive. But this is to exercise the business logic. So we're trying to exercise, did we correctly implement the business logic for the house purchase rules? There's one last decision table in the collection. This is from the chocolate wrapping device, the Wrap-O-Matic that I keep talking about, the fictitious chocolate wrapping device. And there's certain things that happen, right? If you remember, the Wrap-O-Matic had in it many conveyor belts. And bear with me for a second here. There were many conveyor belts in the Wrap-O-Matic. You see the little Wrap-O-Matic picture here. There's many conveyor belts, and each conveyor belt could have different types of chocolates. And we basically wrap the chocolates with paper, and then we put ribbons on the chocolate, and there's different types of ribbons and different types of paper. So there's certain rules about the Wrap-O-Matic that are built into the requirements of it. It's part of the Wrap-O-Matic. We call them the wrapping rules. So one wrapping rule says you're not allowed to apply ribbons to unwrapped chocolates. A ribbon will never touch directly the chocolate. There has to be some sort of paper around the chocolate before you apply a ribbon. So you're not allowed to put ribbons against chocolates directly. You're not allowed to put metal ribbons on hollow chocolates ever. That would crush the hollow chocolate. You're never allowed to put metal ribbons on a hollow chocolate. And then we have a few wrapping algorithms that the machine is going to use. So if we have tissue papers as wrappers, then we're going to use what's called the gentle wrapping algorithm. Whenever we have tissue, we have a rapid algorithm whenever there's no ribbons and no tissue wrappers. So just regular paper would be the rapid wrapping algorithm. We have a gentle algorithm whenever hollow chocolates are tied with ribbons. And otherwise, we have something called a normal algorithm. So rapid, gentle, and normal algorithms. And then rules about hollow chocolates. This then can be represented by a decision table. This is a reduced decision table that describes the conditions. The input conditions here are the viscosity, ribbon, and wrapper. So the viscosity, ribbon, and wrapper, and the only viscosity that matters, is it hollow or not, right? And for the ribbon, is it metallic, none, or other? Those are the things that matter. And then the possible actions are: we disallow the configuration, and if it's allowed, we might choose a rapid, normal, or gentle algorithm. So the decision table should never have something that's allowed, disallowed, and having a algorithm here. So this case here, there's a mistake in the table here. Just look at when it says disallow for rule 6, that means that we shouldn't have a gentle algorithm, because there should be no algorithm in that case. So that's the wrapping rules for the Wrap-O-Matic described in a 15-rule decision table. And thank you very much.